Hi everyone, I'm Tamil. Today I introduce RadarHand, a wrist-worn radar for on-skin proprioceptive gestures. And here are my co-authors of this paper. And touch-based interface is a popular choice among smart mobile devices and smartwatches. However, interacting with them in an ice-free condition is a very difficult task due to lack of haptic feedback or any distinct visual cues. We could consider mid-air gestures. However, we have to repeatedly look for visual cues or our hands get tired. So we want to design gestures that are more intuitive and reliable for smart mobile interaction. So we introduce proprioceptive gestures. We rely on proprioceptive sense, one's ability to perceive each body parts without any visual cues. And we can utilize this particular sense for gestural interaction in a limited interaction space for a wearable interactions. And we particularly look at back of the hand which has quite few distinct tactile features such as joints, knuckles, and nails. In RadarHand, we particularly focus on designing a bimanual hand gesture interaction at the back of the hand. Many previous works have already utilized this back of the hand for gestural interaction for smartwatches. However, they rely on acoustic sensor, which might be susceptible to audio noise, or when they rely on computer-based sensing, sometimes they rely on privacy concerns and immune to light changes, and IMU might susceptible to motions of the users. So we primarily utilize Google's solely radar sensor, which is immune to climate and acoustic noise, less concerns in privacy because it's just basic radar electromagnetic sensor and has a wide spatial sensing, and can be very less, can take a very less small form factor and in a low computation form. And this is a particular sensor that we utilize for this RadarHand project. And it has a 110-degree of field of view with 3 receivers and 2 transmitters, which can able to measure minute gestural interaction in the space. So in order to fully understand utilizing proprioceptive gesture and utilizing radar for smartwatch interaction, we conducted 3 extensive studies. First study is how do we utilize, how do we understand one's proprioceptive sense for backhand interaction. So what we did basically is we put users in an end-back task. We hide them in front of a end-back task and ask them to tap at the back of the hand and use OptiTrack to track their fingers. And we also, in order to induce proprioceptive sense, we want to use users put them in a high cognitive load so that they naturally, they don't actually focus on tapping it. They are answering the end back and touching the simultaneously. And also, after this particular experiment, we also asked subjective measures. We designed, based on previous past works, conventional smartwatches like tap gestures, swipe gestures, and slide gestures. How can we utilize it in this particular RadarHand scenario? So we created a gesture set and asked participants to rate each gesture sets at different fingers based on usability, memorability, and social acceptance. Our quantitative results, that is from the hand tracking study, we utilized Fitzlaw to measure how easy to touch at which point of the back of the hand. And thumb was the most easiest for the users, and the pinky was more hard. The corner red color ones are the more easier to reach or more easier to place, do gestures over there, and followed by index, middle finger, and last pinky. And this, surprisingly, this was also matched with the qualitative study where the users preferred performing gestures in the thumb area, followed by index, middle finger, and pinky. However, there was one contradicting in is users prefer to perform most of the gestures in the knuckle because of their unique tactile feature it can afford. But when they performed in a quantitative way, it was actually harder to reach compared to the nail. Followed by that, we collected data to create a machine learning model that can understand these gestures in real time. So to make a very robust model, we recruited around 46 participants, and in front of the sensor, we placed different materials like glass, cloth, and different materials that you can find it in everyday scenarios, and asked them to do all these gestures 10 times. And apart from that, we collected some background data to train a machine learning model. Here's the overall view of this study, where we computed all these data, split them into 2-second window, where each 2 seconds contributes to one particular gesture, and trained a machine learning model to infer. We utilized the deep RadarNet architecture and fine-tuned for our condition. Followed by that, based on the study one quantitative and qualitative results, we designed around 27 gesture sets and 2 generic gesture sets. The 27 discrete gesture sets are the ones each have different number of gestures based on the user's preference as well as their fits index of difficulty. And the generic gesture is a combination of all gestures that give us. Here's a demo of the system that is working in real time. Yes. Following this, we ran a real-time evaluation to understand the full potential of RadarHand. So what we did is, we recruited 12 more participants who have never experienced RadarHand, and we set up a remote monitoring logging system with an attached. We use Pixel phone as a smartwatch to represent as a smartwatch, and the whole machine learning model was running in the inference in the laptop behind where users were wearing it. And we asked them to do everyday tasks like working in the desk or moving around in the campus. And there is a logging software where they can also log all the information about what they were doing when the gesture was predicting and what gesture was predicting. And for this real-time evaluation, we chose 2 particular gestures from our various gesture sets that gave best accuracy. One is gesture 25, and another was generic gestures. And the discrete gestures has 8 unique gestures with a classification accuracy of 93%, and generic one with a classification accuracy of 92%. Furthermore, in order to understand the effect of background noise, because most of the RadarHand previous works haven't explored about much effect of background noise in real day-to-day life. So we created 2 kinds of interaction. One is active interaction, where user initiates the interaction with the smartwatch, and it was being predicted by the system. And the reactive ones are where user prompts or the system prompts the users to interact, such as a call is coming and you have to attend the call by swiping up or swiping down. So following a detailed analysis on live gesture classification, the active interaction with background classification got less accurate compared to the one with reactive interaction, mainly due to difference in the gestural performance directions by the users. Some users performed in gestures either in a different way that wasn't trained during the training set, and most of the time, the false gestures happen by the active interactions with background. Following this analysis, we created a design, we came up with a design guideline for future RadarHand, future works where people, if they want to introduce radar-based signals for smart mobile interaction, what are the guidelines they can look after? So few of these guidelines are thumb performs best in terms of proprioception and gesture response time, even under high cognitive load. And mostly tapping gestures is most preferred ones compared, and most preferred and most best performing compared to the knob gestures. And if you have any gesture that are similar, avoid placing them in the same area. Followed by limiting similar gestures again in the same region would be difficult. And we designed around 29 different gesture sets, and each can be used for different contexts. For more details, you can check our paper. And we have given generic and proprioception, where generic can be on-the-go message notifications, whereas proprioceptive are ones where context-specific, like music apps and other stuff. Followed by, we envision RadarHand could be a proprioceptive alternative to computer-aided design softwares, or it can be a gesture input for hand tracking in XR space. In summary, in RadarHand, we introduced bimanual gesture interaction for smartwatch, and we conducted 3 different studies and formulated design guidelines to present radar-based interaction for smart mobile devices. Here's a link to our paper, and that's it. I was in time, right?
Hello, thank you for the great talk. I'm Xiang from KAIST.
Yes.
I have just 2 questions. The first one is that have you tested this system on the noisy environment, for example, in the nearby movement?
Noise environment?
So noisy environment, for example, the nearby movement, if there is the around the hand gesture within the...
Yes.
Yeah.
So when we trained the machine learning model, we asked participants we also trained a specific background class where we asked participants to move around with the sensor for a long time, and we asked them to type during the computer. We collected a lot of background data, basically, and we trained the machine learning model to classify this background data as well as these gestures that when happens.
So those system is robust to those nearby movement? Okay, got it. Thank you. And the second question is that how this system knows the timing of the end of gestures?
So what we did is we kind of computed a moving average system. So we continuously monitor the range Doppler data's amplitude. So in the first step to distinguish between the background as well as when the user is gesture is most of the background data noise are easy to identify based on the amplitude itself and their phasic value of the range Doppler complex. However, when you look at the gestures, when users are about to perform, they come closer to the hand and in a certain speed. And you can, we collected around 46 data to identify what is the minimum threshold. And we use that threshold to identify whether the user is approaching for performing gesture or not, and took that window to predict.
Then what is the threshold of in this system?
Huh?
What is the threshold of the...
The threshold of this system, I would probably I have to look back and say.
Yeah. Thank you.
Hi, thanks for a wonderful presentation. I'm Mia. I'm a PhD student from NUS Singapore.
Yes.
So I think I have a few questions.
Yes.
The first one is, have you test with like the activities when the person is like moving, for example, probably not moving, but like an environment where like on the cars or in the bus or like have some activities?
No, I haven't tried that in a different environment.
Okay.
It was all either in a lab or around the campus.
Okay, so like, what is your hunch about like how robust it's going to be if we test in like that environment?
I would say that if we have enough data to the model to recognize at different locations and different spaces, if you train in a way, it could work. But with the current setup, I think I wouldn't say it won't work at the best because it haven't seen that enough data to, because this particular system highly relies on machine learning, and machine learning requires a lot of data.
I think like the second question I have like regarding the machine learning. So like the accuracy of the model is like tuned to the personal gestures, or it's like you collect a lot of data across participants and then you just apply the model trained on like the general data on like a new person kind of data. Like do you have like a personalized model and then like cross participant validation?
It's a cross-validation, like it's not personalized. So it's more generic, like I trained it across all participants and deployed it in a new world. So it's more like in the wild exploration.
That's cool. Thanks.
Thank you. Thank you for great questions.